Okay, welcome back, folks. In this video, what we're going to do is discuss bell curves and the empirical rule. So two big concepts here in statistics. So first of all, in order to properly understand bell curves, we have to figure out where they come from. So let's take a look at this. This is something that we saw before. It's a frequency table. I've got 5 classes, A, B, C, D, and E. Doesn't matter what they are. They could be letters and first names. It doesn't matter. It's the classes that I've assigned and that I've given them their frequencies. Now, this is a table that I built specifically, right? So this is data that you might see, you might not see it. It doesn't matter. I built this specifically for this specific picture. So I have my frequency table, and from that I have a roughly hand-drawn histogram. Remember, the heights of the bars of the histogram tells us how many of each data point there actually are, how many of each class there are. So let's take a closer look at this histogram that we have here on the right side of the screen. I'm going to copy this, I'm going to blow it up so we can take a closer look at what actually is happening here. So here I've got my histogram. What's actually happening with the histogram, it's actually kind of cool. All of our data points are actually represented right here in this picture, right? We know that this height of 1 means there's exactly one thing in category A. This height of 2 means there are exactly 2 things in this category B. Altogether, at this point, we have 3 total data points, right? Because I've got 1 data point in the first bar, 2 data points in the second bar, so altogether 3 so far. I know that I have 4 data points in this middle bar here, the highest bar. So altogether I have 3 from before plus 4 more makes 7 total data points. Continuing right along here, I've got 2 more here and 1 more here. Altogether, I have 13 data points, and they're all represented right here in this picture. The histogram encapsulates all of the data points in our data set. Now, something I want to point out to you guys is that this shape, where the tallest chunk is in the middle and it starts to taper off on either side, is a shape you need to become very familiar with. This frequency table that I built is not an uncommon type of frequency table that you'll see, where the lower numbers are on the top and the bottom, and then as you get closer and closer to the middle, the data points start to increase. This general shape should look somewhat familiar to you when I draw the following. This right here is the origin of the bell curve. The bell curve, or this bell-shaped curve that fits outside of this perfectly symmetric histogram, is kind of the foundation of everything that we're going to be doing going forward in this class. So this is the origin of the bell curve. This is the thing that we're going to be looking at a lot going forward. And the important thing to remember about the bell curve is that all of the data is represented by this shape. All of the data is kind of wrapped up inside of this bell curve. So if I were to look at just a picture of a bell curve, and I were to have these classes A, B, C, D, and E, we would see all the data points are trapped underneath of it, meaning the height above C represents all of the data points that satisfy category C. The height above B is all the data points that satisfy the category B. The height above D, etc., etc. Now, what is this primarily useful for? This shape is often used to describe things like grades, right? Think about it like this. Instead of using E as the top category, what if I used an F? The grades that we follow in the United States are A, B, C, D, and F, right? Now, think about the distribution of grades in a class. The majority of people fall right around C. Right? The majority of people usually get a C in the class. That's considered the average grade, right? This grade right here is the middle. The majority of people, the highest frequency, the highest point on the curve, is going to be at C, or the average. And then it starts to taper off, right? Fewer people get a B, and fewer people get a D, then get a C. Even fewer still get an A and an F, right? Because if everyone was passing with an A, the teacher would be kind of suspect. And if everyone was failing, well, then that class has probably got some major problems. So very few people pass with an A and very few people fail. That's why it's very low right here. That's why the histogram bar was very low here. Similarly, very few people fail. That's why the histogram bar is very low over here. But the majority of people pass with a C. the majority of people are at the average. Now that's an important thing which I just pointed out there. The average is right smack in the middle of this bell curve. C is the average or the mean. Now the mean or the average, we typically say mean going forward, we express using this symbol mu. It's kind of like a funny looking U, but it's the Greek letter mu, mu. We use that to represent the average. When we're looking at bell curves, we want to think about it being centered around the average. The data is centered around the average in these bell curves. And another thing to mention here about the notation here that associates with the bell curve and with statistics in general is the notation that we use for standard deviation, that thing that we've mentioned a few times but have yet to really address. The standard deviation we abbreviate with the symbol sigma, the lowercase sigma, which is a Greek letter. Once again, this is the lowercase version of it. It's kind of like a circle with a little line off of it. It's like a guy with a hat on. That's the symbol we use for standard deviation. Now, what the standard deviation is, we're going to get to that in just a second, but there's one thing we need to discuss first. In looking at this bell curve, it's one thing to know that the mean is in the middle, but we also want to know how spread out our data is from that mean, and that's kind of the language you've been using for standard deviation, so let's tie that all together. So what we need in order to tie that all together is something called the empirical rule. The empirical rule is the kind of guideline that gives us a sense or a standardization of how far our data is actually spread out, or what percentage of our data is actually clustered around the mean. So the first thing that we need to know about the empirical rule is this. The first thing that it tells us is, within plus or minus 1 standard deviation from the mean is 68% of our data. Now I'm going to give you all the rules now. I'm going to give you all the pieces of the rules now, and then we're going to go over what that actually means. Don't worry. The empirical rule says, first of all, within plus or minus 1 standard deviation from the mean is 68% of our data. The second thing that the empirical rule tells us is within plus or minus 2 standard deviations from the mean, which is again that mu symbol, is 95% of our data. 95% of our data is within 2 standard deviations on either side of the mean. Lastly, what it tells us is within plus or minus 3 standard deviations from the mean is 99.7% of our data. Okay? The empirical rule tells us these 3 things. That within 1 standard deviation of the mean, on either side of the mean, is 68% of all of our data. 68% of it is within 1 standard deviation of our mean, plus or minus that. Within 2 standard deviations is 95% of our data, and within 3 standard deviations of the mean is 99.7% of our data. Now, hold the phone. What the heck does all that mean? Let's take a look at our bell curve one more time. We know that the bell curve is centered around that mean. We know the mean is in the middle. We've talked about that already. What the standard deviation is like a measuring stick, and the measuring stick varies for every data set. Every data set has a different standard deviation. Sometimes they have the same calculation, whatever, but it's all calculated dependent upon a specific data set. And what that is saying is this. Let's pretend that the standard deviation is like our ruler, our measuring stick. It's our standardization. It's what we measure all things against. Think about standardized tests, right? That's our benchmark that we use to compare ourselves against an average. Same thing with standard deviation. It's our benchmark that's comparing how far out our data is. So this ruler is our standard deviation bar. Okay? And we have one on the right side of the mean, and we can put one on the left side of the mean as well. And what we know based on the empirical rule is that we're saying within 1 standard deviation on either side of the mean. Meaning, if I take my mean and I add 1 standard deviation to it, and I take my mean and I subtract 1 standard deviation to it, between those 2 numbers, this here is 68% of our data. Okay? Think about the histogram again. Think about the histogram. Remember, we had all these bars that represented all of our data. So we're saying that between, let's say, this number here and this number here, these bars that we're shading in, these portions of these bars that we're shading in, is 68% of our data points. 68% of the class, 68% of the car, 68% of whatever that we've looked at in our data set are between these two values, which are one standard deviation on either side of the mean. Moreover, what we have is this. If I keep putting standard deviation bars on either side of the mean, so now I've got two standard deviations. Whatever that standard deviation value is, whatever we've calculated that to be, within two standard deviations on either side of the mean, so the mean minus 2 standard deviations and the mean plus 2 standard deviations, within those two, I'll do that in orange, between those two values, everything trapped between them makes 95% of the data. Lastly, we know if we put a third standard deviation bar on either side of the mean, one on the right and one on the left, right? So if we measure even further out, we go an additional standard deviation beyond the mean, we know that between these values here of the mean minus 3 standard deviations and the mean plus 3 standard deviations, between these two values represents, well, it looks like basically all of the bell curve, right? In fact, it's 99.7% of our data are trapped between these values. So the standard deviation is our measuring stick that tells us how spread out our data is. And it tells us that within certain ranges, within certain standardized ranges of the mean, are certain percentages of our data. So let's take a look at a concrete example with some real numbers and try to make this make a little bit more sense. So let's say in our data set, we know that the mean is equal to 10 and the standard deviation is equal to 1. The mean is 10, the standard deviation is 1. So we have our bell curve that is centered around the mean of 10. We know that with the standard deviation of 1, if I add 1 to 10, I get 11. If I subtract 1 from 10, I get 9. The empirical rule tells us that within one standard deviation on either side of the mean represents 68% of the data. Interpretation, let's say this is the number of minutes someone spends driving to work in class, right? You've calculated, you asked how much time you spend driving to work. Asked everyone in your class that, and we got a whole bunch of numbers. The average that you calculated was 10 minutes driving to work. It's very lucky. I drive much longer than that. What we know is that 68% of people said that they drive between 9 and 11 minutes to work. That's what the empirical rule tells us. That's what the standard deviation tells us as well. Take it one step further. Let's bump it out another standard deviation. So we subtract another one on the left, we add another one on the right. So we're looking now between 8 and 12. So between 8 and 12 is 95% of our data, meaning 95% of the class reported that they drive between 8 and 12 minutes to work. Some people said 8, some people said 8.5, some people said 9, some people said 10, etc., etc. 95% of people, they gave you a number between 8 and 12. Taking this one step further, one more standard deviation on either side, we subtract one on the left to get 7, we add one on the right, get 13. The empirical rule in the standard deviation tells us that 99.7, nearly the entire class, reported a time between 7 minutes and 13 minutes. 99.7% of the class told you they drive 7 minutes, 7.5 minutes, 7 minutes and 45 seconds, 8 minutes, 9 minutes, 10 minutes, 12 minutes, all the way up to 13 minutes. 99.7% of the class reported a time between 7 and 13 minutes driving to work. The empirical rule is a powerful thing because it tells us about the distribution of our data, and the standard deviation is our measuring stick that helps us to do that. So this is your crash course on bell curves and the empirical rule. Check back in for more examples, guys. I'll see you next time.